Hi, welcome to this tutorial on finding the mean and variance for continuous random variables. And that's the aim of this tutorial, just to get you the formulas that we use. In other videos, what I'll do is run through an example or two on using the formulas to calculate the mean and variance. Okay, so let's see if we can establish what these formulas are. Now what I've got here is a spinner, and on this spinner you can see the numbers 1, 2 and 3, the scores. Alright. Now if I was to spin this spinner, then the score that you get would be the one opposite the arrow when it stops. So you could get 1, 2 or 3, and you've got the corresponding probabilities down here. Probability of a 1, 3/8. There's 3 ones there out of 8, right? And these particular scores are discrete random variables because you've got the exact values. When it comes to continuous random variables, however, you can't give the exact value. Take for instance this particular distribution here, this probability density function. It could be, say, that of the lifetime of a particular component lasting between 0 and 2 hours. Now the probability of it lasting, say, for 1 hour would be 0. You just cannot work out the probability of it being an exact value. However, you can work out the probability of it being within a certain interval, and that interval could be something like this. Okay, like that. That area would give the probability of lying between a certain time and another time. Now we should know that the sum of the probabilities for a discrete random variable always total 1. And so that means that we can write this as the sum of the probabilities that correspond to particular observed values x, and if we were to sum those probabilities it would come to 1 for all values of x, and we write this symbol here for all values of x. You can see that here 3/8 plus 4/8 plus 1/8 comes to 1, and it would be true for any discrete probability distribution. When it comes to continuous random variables, we know that if we were to sum all the probabilities from, say in this example, 0 to 2, that would come to 1. But in general, if we were to sum all the probabilities from the lower limit of the probability density function up to the upper limit, which I'll call -infinity to infinity, then the sum of these is given by the area under the graph, which is the integral of f of x with respect to x, and this would equal 1. Now when I compare these two results, there is quite a bit of similarity. When we sum all the discrete random variables and compare that to summing all the intervals here under the graph, it's as if this is an infinite summation. It's as if the summation sign here is replaced by an integral sign. And when it comes to the probability of a particular observed value, then that corresponds to the probability density here, almost as if we're looking at the area in a thin strip. And it's this comparison that we can draw on when we want to find the other formulas. Now you should know that the mean of a discrete random variable, often written as E of x when you have a probability distribution table, and that is calculated as the sum of all the observed values x multiplied by their corresponding probabilities, and we sum that for all values of x. So for this particular probability distribution, the mean E of x would have been 1 times 3/8 plus 2 times 4/8 plus 3 times 1/8. So when we're trying to find the mean for a continuous random variable, the mean E of x would be equal to, well, we can use these results up here. We've got a summation here, and the summation for continuous random variables is the integral going from minus infinity, the lower limit of the probability density function, to the upper limit. And then we had x times the probability of x, so x there, but the probability of x corresponded to fx dx for the continuous random variable, so we have fx dx. So we have a formula now for the mean E of x then for a continuous random variable. You should also remember that when you were working out the variance for a discrete random variable, often written as var x, this was equal to E of x squared minus E of x, all squared. Now what was E of x squared? E of x squared was the formula, the sum for all x of x squared times the probability of x. So for this particular probability distribution, it would have been 1 squared times 3/8 plus 2 squared times 4/8 plus 3 squared times 1/8. That would have been E of x squared. So when we're doing the same thing for continuous random variables, E of x squared would be worked out by doing, instead of the sum, the integral now from minus infinity to infinity, from the lower limit of the probability density function to the upper limit, of x squared times probability of x, which we now know is replaced with f of x dx. So once you've worked out E of x squared using this particular method, substitute it into here, you've got E of x, the mean, square it, and you've then got the variance of x for a continuous random variable. So hopefully I've been able to show you the similarities between discrete random variables and continuous random variables and the formulas that we use. Well, that brings us to the end of this tutorial, which, as I said before, was just to establish the formulas. In some of my other videos, what I'm going to do is a few numerical examples using these particular formulas to work out the mean and the variance. And so I hope you'll look at those and be able to understand how to do questions like this.